Too early for this, but let's give it a shot. So the only real announcements this morning are drop-ins are still happening. Obviously, they're going to be happening every day at noon. Okay, everyone please. So we've all done trig before. We've got to be hard to avoid. And like everything else, we're starting again. It won't be ultra slow, but we'll also look at what's its use, and it may have never made sense in the first place. We'll find out. Note that we're only doing 1 week of trig, right-angled trigonometry. There's non-right-angled trigonometry, sine or cosine rule. No, we're just doing 1 week of right-angled stuff. So, firstly, just the conventions, a bit dull, but just how we name a triangle. It's a standard no matter what you're doing with triangles. Basically, not that it's right versus wrong, but the convention is in the main dumb thing is we'll call corners capital letters and edges small letters. And just note the most relevant thing out of this is just that they're opposites. No, not interested. Okay, so which side's which? They're just opposite the sides. The side is opposite the angle and vice versa. Okay, so that's how you label a triangle. That's how we'll label it. But sometimes we'll also you might use an alpha there, or a beta there. Angles can be named from the external point or in there. It's going to be fairly obvious. The only other thing in this slide, the hypotenuse, this side and this side can have different names. We'll get to it soon. Sometimes they're adjacent, sometimes they're opposite. Okay, there's reasons for that. But the hypotenuse is fixed. In a right-angled triangle, the hypotenuse is always the longest side, and the longest side is always opposite the right angle. Okay, so one thing that's fixed in the name of a triangle, not the letter, is just hypotenuse is the longest side. Okay. Now, also, we do it a bit in these slides. Instead of calling this side C, I could call it AB. You say, well, can you call it BA? Yeah, you can call it BA, but we'll normally do it just alphabetical order, just linking the corners. Again, I think it's fairly clear that if we're talking about a side length AB, it's clearly the length from A to B. And yes, this angle here, I could refer to that as BAC, so it's just me drawing if I go BAC, yeah, I'm referring to that angle, so we write angle BAC. And in these notes, that happens a fair bit. And if I write angle CAB, just as good, okay? But when you get to the worksheets, we get lazy, and basically I'll just be saying angle alpha, okay? Or unknown angle, and you might call it whatever you want. I could call that angle CBA, or if I've got a picture, I could just stick a theta in there. Now, we don't use many of the Greek letters, and I don't know all of them, far from it. But this is the most common one used, okay, for angles, theta, and then just good old AB in the Greek alphabet, alpha, in other words, fish, and beta. So theta, alpha, and beta are just common ones, okay? You can call it X if you want. Just normally give X and Y and that to sides. So there's just how we are going to describe our triangles. Now, Pythagoras is one of the first triangle men. He was into them, and he came up with this rule, okay? And we will have seen it before. Now, note the letters aren't important. What side gets given A, B, or C, there's no convention to that. The only convention is you've got to have the hypotenuse by itself. As in, I don't care what, I could just write that the hypotenuse squared is equal to a side, I'll just call it side 1 squared plus side 2 squared. Clearly, if I'm calling them side 1 and side 2, it doesn't matter which order I put them in, plus is plus. The only thing that matters is your hypotenuse, the odd one out, is it the one by itself? So the rule is that the longest side squared is equal to the sum of the shortest side squared. Not too shabby at 570 BC coming up with that. And he did it by this. This picture explains his thought process about doing it. He said, well, look, if I've got a triangle, if I made a square out of this triangle's side, and we've just picked a fairly special triangle, but yes, it's a right angle triangle, that square would be 3 by 3, which is 9 blocks. This side length, if it's 4, would be 4 by 4, which is 16. He found that if you drew a triangle that's lengths of sides of 3, 4 and a hypotenuse of 5, well, 9 squares plus 16 squares equals 25. So yeah, this side squared plus the other side squared did equal the hypotenuse squared. So that's how he worked it out, and since proved that it's true for every single right angle triangle. So, and the direction we're going in, there's a little bit on it, not much, but you think, well, what's so special about triangles? Yeah, it's huge. I mean, especially, let's just go straight to what matters to us fairly well at the moment, GPS. It's all triangles. Okay, everything we know about the galaxy, everything we know about distances, mapping and all of that, it's all making triangles from here to a known point to an unknown point, and I can work out distances. A bit more on that later. There's another visualization. The same thing showing that the area that was formed by this large square, because we've broken up, that bit goes there, and those bits form that. So yeah, this side squared equals that side squared plus that side squared. All right. So just some examples. If we're looking at that, as long as you just pick out the hypotenuse is the odd one out, we're all good. So the hypotenuse here, we're calling it AB. Clearly this is AB. So we just say AB squared is equal to, and again, the lettering, whether you might say A squared equals B squared plus C squared, doesn't matter, as long as I'm clearly calling the hypotenuse this one. So AB squared equals 6 squared plus 9 squared, absolutely. 6 squared and 9 squared, we know is a 36 and 81. We're calculator now. 36 and 81 is 117. Just a heads up, 117 will have to be one of the trap answers in any multiple choice. Don't forget that if you end up with an answer of AB squared equals 117, you weren't ever after AB squared, you're after AB. So the little bit of algebra we're doing in this semester, get rid of the squared by square rooting. Now, I've written that as a technicality from last semester for those that did it. Yes, last semester we got to the point when we said, look, if x squared equals 9, you've got two answers, and we had this, like I was saying, put it on a resource sheet. If you've got a squared, give us a plus or minus in the answer, because yes, minus 3 times itself is 9, 3 times itself is 9. I've written it there, but we don't have to, because we're talking distances. Okay, there's no not minus distance. So we are back to maybe where we used to be, just to think if x squared is 9, just x equals 3. That'll do when it's a distance question. I've straight out ignored the minus answer. So you're not required to put that in the working. If you went straight to that without the plus or minus, you're doing a distance question, okay? No one cares. So it's an applied semester where the plus or minus answers just of no interest to us, okay? Not wrong if you do, not wrong if you don't, as long as you state that the answer is 10.8. Now, in this case, there were no units given. I've written the word units there. That's not essential either. What is essential is if the question did have units. If I was told it's 6 metres and 9 metres, don't just give the answer as 10.8. Give the answer its units. But if there's no units, we can just deal straight in numbers. It's all good. This one, there's no difference. It's still the hypotenuse is the odd one out. It's still the hypotenuse which is unknown. So my hypotenuse squared, see, I could write AB squared equals, blow it, I just don't like it. You give me a picture, I'm just going to draw X there. I just want it quicker. Okay, there's no problem obviously calling it AB, or call it little side C. I've just got to have it, I just like it just being good old X squared equals. I've got a 6.5 squared plus a 4.2 squared. And there's no problem with going straight. We've got the calculator now. X is the square root of all that. And I would just go straight to the calc. I would go to a 6.5 squared plus a 4.2 squared equals, don't forget, square root that answer because that's x squared. And it spits out, syntax error, what do I press? Square root answer equals. So it's spitting out, 7.73886. Again, we don't have to write that. I'm just saying what the calculator put. We weren't told how to round it, so just do as you feel, okay? Look, 7.7 looks pretty reasonable to me, but whatever you do, remember the two things. One, if it had units, keep them. And two, if you do round, if it's something that needs rounding, just say what you did. 1 dp. Cockroach. Awesome. Okay, so, but if you did 7.74 to 2 dp, yep, fine. You could do 8 centimetres to no dp, but that's pretty dodgy. At least give it a decimal place or two. But great, yes, that's using old Pythagoras' rule. Next example probably is, what if it's not the hypotenuse, it's unknown? Yep. Okay, so it's still exactly the same thing. It's just here's my sides that are the other sides, and here's my odd one out, the hypotenuse. You do the same thing, we've just got to do a little bit of algebra. Now, it doesn't matter. Some people want to rearrange the formula first and then sub in. Some people sub in, then rearrange the formula. It makes no difference. I'm just going to do it straight up. Just write out what this says. And what I always write out is hypotenuse squared equals the other two squared and added. So the hypotenuse squared is the odd one out. Yep, so it's out by itself, the longer side squared. It's equal to 3 squared plus y squared. So in other words, I've started exactly like every other question. No matter what's unknown, I just put the unknown where it is. It wouldn't have mattered which one of them I had the y at, because it's a plus. Then I'll just go 25 equals 9 plus y squared. And again, the little bit of algebra that we're doing, but it is pretty constant. I don't want to get rid of the square root first, I get rid of the easy stuff first. On this side, the easiest thing to get rid of is that 9. So I'll take a 9 away, leave me 16 equals y squared. Again, I'm having flashbacks of Sem 1, but I don't care about the plus minus. I'm fine to just go, well, y is the square root of that answer. Y is 4. That's it, y is 4. No rounding needed. I check for units. Okay, so that was that same one I was talking about Pythagoras used. It's not usual, that's a Pythagorean triad. There's a few triangles that just have really nice numbered sides, and you'll see them in, you'll see them in heaps of exercises just because they're pretty. So that one happens a lot. 3, 4, 5. Another one that's nice and gets used a lot. I'm not saying this is, you need to know them. We work it out. But just for trivia, 5, 12, 13. That's another one you see a lot. 5 squared is 25, plus 12 squared is 144. They add to 169. Root 169 is 13. So just, they're two Pythagorean triads, two well-known ones that just have really nice length sides. It works for all others as well, but like say I did, there's a nice triangle that's just 1 by 1, but the length of that other side, well, 1 squared is 1, plus 1 squared is 1 is 2, and the square root of 2 is, okay, square root of 2, it's fine, that's a perfect triangle. Its hypotenuse just happens to be root 2 long. We're not going to avoid that, that's okay. If that was in metres and that was in metres, we gave the answer is root 2 metres. Nothing wrong with writing that, okay? I could go to the calculator and say, look, it's 1.4 metres to one decimal place. We've got the calculator which will tell us what root 2 is, okay? So yeah, most of them aren't pretty, but there's nothing wrong with a root answer. So the example that we've got on that, there's the pretty version behind. Determine the length of BC. Okay, well, again, I'm just making sure I know which one's the odd one out. The hypotenuse is the odd one out. The hypotenuse, when squared, is equal to, again, I'm just going to chuck in an x there because it's clearly this side I want. The hypotenuse squared is one side squared plus the other side squared. 389? How's the memory? 289. Terrible. 289 equals 144 plus x squared. If I take that away, I've got 145 equals x squared. You can see that one's 289 minus my 12 squared. That's not going to be pretty. So I've got two options. X equals the square root of 145. As horrid as it looks, is perfect. That answer is perfect. I'd have to put my units next to it. But there's nothing wrong with that answer. But also the rule, or the answer that says more to me, 12.04159, blah, 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 12.0, it was followed by 4, so I didn't round it up, is 12.0 metres to 1 dp. Just 100% the same as each other, okay? And if we're doing multiple choice, well, which one's there? If you're looking for 12 and it's not there, you know, root 145 might be there. Okay, so that's our Pythagoras' theorem. So that was the earliest. That wasn't technically trigonometry yet. It was just starting off on triangles, so we actually haven't hit trig yet. Degrees, minutes and seconds. Okay, so clearly we're going to talk about angles, and in terms of angles we need to say sometimes we're going to be more accurate than 30 degrees, 40 degrees, 45 degrees. Between 45 degrees and 46 degrees there's 45.5 degrees. And so we want to split it up further. Now we know there's 360 degrees in any circle. Okay, if you do a 360, you'd come right back to where you started. It's 4 90s, a 90 and 90, so 4 90s is 360. There's a circle. So we know 1 degree is just 1 3/60ths. Okay, we're probably more used to like a 90-degree angle. Whenever we refer to that, we'll use the term perpendicular. Not really much in this course yet, until we get to graphing. But yeah, perpendicular just means if two lines are perpendicular, it just means they're at right angles. We just put that little square in there saying, yep, it's right angles. So you can see that 1 degree is not much. That's a bit over the top. There's meant to be 90 of them in a 90-degree angle. Okay, we've got some concept. There's a degree. Why 360 degrees? It seems like a pretty random number, but it came from, once again, historical maths. And part of what they did then was when we looked at different base systems last semester, not again, they used a base 60 system. A lot of things we've used is in 60s, okay, which is the same in the minutes is out of 60. Our minutes, apart from degrees, our minutes in time is 60. Our days of the year is, well, it's 365, but originally thought to be 360. So we did a base 60 system for a while there, and we've still got some of it with us. But anyway, that's why 360. That's why. So fraction of degrees. Now, firstly, if we've got an answer, 37 degrees, 42, now that means minutes, and 17, that means seconds. I forget the proper name. Apostrophe? Anyone? Academic literacies? Double apostrophe? Okay, I'm making them up. I don't know. I know there was minutes and seconds. So this single dash thing is minutes, the double dash is seconds. So what does that mean? 37 degrees, okay, I've got a concept of that. I know that that's 90, 45's halfway, so 37's, okay, it's something of that order. 42 minutes, like our time, it means out of 60. Okay, so 42 minutes out of 60. So that's close to 3/4 of a degree. This is sort of like 37 3/4, okay? So, of course, 42 out of 60, 45 out of 60 is 3/4. But anyway, as long as we know that this one, and seconds is also out of 60. Okay, so that's much more accurate than we particularly care about in what we're doing. But it really means 37 degrees and 42/60th of a degree and 17/60th of a minute. The calculator spits it out for us. Look. The calculator initially, well, we'll look at the second form. See, I was saying it was around 37 3/4. It was closer to 37 7/10. But let's look at these two answers. If we put them on the calc, then primary dot camera, what was it? 37.7047. 37.7047. Okay, if I press the degrees, minutes, seconds button, which will be different on all of us. Hopefully it looks like that, degrees, minutes, seconds. That will then spit it into the other form, okay? So we're not manually calculating anything, as long as we know where our degrees, minutes, seconds button. On some calcs, it's an arrow pointing to the right. But anyway, just check on your calc or ask us in the tube. So both of them are the same answer. Neither is more correct than the other. But that just says 37.7047 degrees. Fine, there's an answer to 4 decimal places. 37 degrees, 42 minutes, and 16.92 seconds. I'll just call it 17 seconds. Okay? We will have questions that says round it to the nearest degree or round it to the nearest second, stuff like that. Note, when I put 37.7047 into the calc, like if I want to do 45 degrees, I don't have to press the degrees button. I can go 45 degrees is 45 degrees, no minutes and no seconds. But the calc already knows if you stick a number in, it's in degrees because it's got the D there. Don't, it's already started. Your calculator wants the D. It has to have the D up there for this entire topic because if it's not, where is it on this one? Mode? No. Shift mode? There it is. Deg, rad, degrees, radians or gradient. There's 3 settings. We're not going to use the other settings, and hopefully your calculator, it should, when it's reset, be in degrees mode. Radians is another way of expressing angles. It's totally different. So is gradient. So as long as you've got the letter D up the top, all as well. Some calculators, like the shift ones, sharp ones, there's a little button here that says DRG or something, and it's really easy to change it. You don't have to go into the menu. You can just press it and it's changed. So just check for yourself whether you've got a calculator that's easy to change modes. Keep in degrees mode. All right, PC. So when rounding degrees, so we've got to do a bit of rounding. There's only really one concept, and that is if you're, like if I spit out, look at this one's easy. This one on the calculator, what was it, 37 degrees, it was 0.70, blah, 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 blah. It's pretty clear that that is 38 degrees to the nearest minute, because it's 37.7. If it's 37.5, I'd round it up. If it's 37.4999, anything under it, I'd leave it at 37. Same rule as last semester. But if you're asked a question to round this, we've got to think, and it's a trap. Normally, if I saw a 4 after the number, I'd say, down you go. But it's 42 out of what? 60. So that's a round up. Okay, this is unique for degrees. Now, if it's 42 out of 60, clearly the halfway in minutes must be 30. So if I get an answer that's 37 degrees and 30 minutes, if someone asks me, round that to the nearest degree, it rounds up. 30 is the halfway mark. 30 minutes out of 60 is the halfway mark. So 37 degrees and 30 minutes, if someone said round it up, would be 38 degrees, because we said halfway, up we go. If it's 37 degrees, 29 minutes, it stays. That's a 7. Okay, 29 minutes, don't round up. 30 minutes, round up. Same with the seconds. Minutes and seconds are both out of 60. So that's all this text is about. Is saying our new halfway point, if it's not just a decimal, a new halfway point is 30, and 30 goes up. So what would that be when rounded to the nearest minute? Okay, nearest minute means don't give us seconds. And that was the exact example I was talking about. If it's 30, up it goes. 121 doesn't stay. It'd be, sorry, to the nearest minute. I'm looking at the wrong thing. Same degrees. The nearest minute is, do I leave it at 30 or do I take it at 31? What does the 45 tell me? Up. So my only decision was leave it at 30 or take it up to 31, and 45 said take it up. To the nearest degree, to be perfectly honest, I'd just press the degrees, minutes, seconds button and look at it as a decimal, and it would have spat out 121.5, blah, blah, blah. And it would have been very clear to me, if I press that degrees, minutes, seconds button, we'll just alternate between the two forms. I'd rather do it as a decimal. And it would have said 121.5, blah, blah, blah. Clearly it's 122 degrees. But it's the same thing here. 30 says go up. 122 degrees. Okay, so that's our rounding on the calc. All right, degrees, minutes, seconds. Now this is just to say don't forget the old method. And again, often we're just going to see it in decimal format, and I'd rather work with it that way. Okay, to 2 decimal places, there's no change in the rules. 2 decimal places says, all right, don't write anything past that. Leave the 3 or take it up. It's back to good old rules. Take it up to 7. So it's 342.5, take it up. 3 goes to 4. Yep, 342.54 degrees, just a normal decimal number. 2 significant figures, memory tester. Well, it can do much, but it can appear in certain size numbers. We only want to keep 2 figures. So I'm going to keep the 34. Do I leave the 4 or round it up? It's only followed by a 2. Leave it. But that can't be my answer. Remember what we did? We said, yep, we'd give it a 0. We want it to be the same size. So if we're getting rid of numbers, we stick zeros there. It's 342 degrees. It's roughly 340. 340 is the answer with 2 significant figures and maybe some zeros just to put stuff in the right column. But yep, 340 degrees, and there's my 2 significant figures. And the nearest degree is just a good old no decimal places. It's just, is it 342 or is it 343? Followed by 5, 343. All right, so there's our rounding. Yeah, which is important. We want our accuracy. Angles of the calculator, and again, I know that some of this may or may not be deathly dull. You may know it, but so if I'm getting asked to put 37 degrees, 42 minutes and 17 seconds, 37 degrees, 42 minutes and 17 seconds into the calculator, well, on this calc, it's just 37 and the degrees, minutes, seconds button, 42. Now, it still looks like degrees. It's just the way the calculator does it. It's the same button. So whereas that looks like 37 degrees, 42 degrees, and 17 degrees, if I press equals, okay, yep, that's what I was saying. So just degrees, minutes, seconds button you press after each one you put in. That's it. And I can still then just press the degrees, minutes, seconds button, and it'll convert it between that form and just good old plain decimal. Okay? Now, on the sharp, it's the same thing. Yep, it's exactly the same thing. It's just literally DMS button, the degrees, minutes, seconds button. Okay, so when we might be asked, you know, here's a triangle, and we're going to do some trig thing on it, and this angle is 26 degrees, 14 minutes. It doesn't have to have a seconds. 26 degrees button, 14 degrees button. There it is. That's it. Okay, so we'll get to examples using it soon. And to convert between them, I already said that you can press that. On the sharp, however, it's a 2-button thing. The degrees, minutes, seconds button itself won't convert it. I think if you press that, it does nothing. You've got to do second function, the version of the shift key. Anyway, again, if you've got issues with the calc, hassle me here or tutors in the tutes. And I've already talked about the degrees mode. Yep, it'll spit out some wrong answers if we're not in it. Okay, trig ratios. I admit I did these only this morning, checked in only a couple of slides, because I thought, look, I've done nothing here about, you know, much background to it. And it doesn't go on for long, and I forgot to put a picture of Neil, but clearly he's there looking. And to prep for this, good university preparation, I watched some YouTube when I went to bed last night. And you know, these two blokes were talking 400 BC and 190 BC. So since Pythagoras was about 550, these two got into trig. Now, trig is a really simple concept. Trig is all about ratios. Trig is like last week. Firstly, what these two did, separately, obviously, was they were the first to measure the relative distance from the Earth to the Moon. So they didn't know the actual distance, but they worked out as approximately 60 times the Earth's radius to get to the Moon. And they were right. And they did that using all sorts of techniques, using triangles. A picture that the Indians came up with later, I thought this was really interesting, that they worked out that the Moon and the Earth, they worked out the actual distance themselves as well. But first what they did was worked out the ratio. They waited till the Moon was exactly half lit up, or as well as you could tell, the naked eye. See how that picture's showing the Moon is half lit up? That was saying that the Earth, Moon, Sun was creating a 90-degree angle. Otherwise, I wouldn't see exactly half of the Moon. So they discovered that when the Earth, Moon and Sun, on that time that it hit a right-angle triangle, or a right angle, they had a right-angle triangle. Then they said, well, they got an acclinemeter and worked out the distance, you know, aimed one at the Moon, one at the Sun, and worked out how many degrees it was between them. And they saw that it was 89.86, not quite 90 degrees, which left a remainder of 0.14, because all three angles have to add up to 180. And then, because they'd been working on trigonometry, which we'll get to, they knew that that made the distance between the Earth and Moon, if that was 1, the Sun was 400 times that away. And again, they were correct. Not bad in the day they were in. So they worked out there was a 1 to 400 ratio between the distance between the Moon and the Sun. So we'll come back to, well, how does that have anything to do with what we're doing right now? Why do we call it trigonometric ratios? Because that's all trig is. If you look at that little triangle, once again, I've picked a nice triangle. Most side lengths aren't as pretty. But if I make a triangle, I don't care how big I make it. But if I make a triangle with a right angle and a 30-degree angle, you can also say the other one's going to be 60. There's no option in it. All three's got it out to 180. But if I make any triangle with a 30-degree angle, this hypotenuse will be 2 times this side. That's just saying the ratios of the sides are 1 to 2. The side opposite the angle is half of the hypotenuse. If I make a bigger one, it might be 2 metres, 4 metres, 3 metres, 6 metres. But all that came out of that, the trig that came out of that was saying sine 30 degrees equals a half. So that statement we'll get to saying we're going to talk about sine of an angle is equal to the opposite over the hypotenuse. So the sine of the angle is equal to the opposite side over the hypotenuse. And since sine 30 equals a half, it's just saying you make me any triangle with a 30-degree angle, I promise you these ratios will be a half. Sine 29 degrees won't be a half. Maybe it's 0.4982, I don't know, I'm making that up. I don't have trig tables in the head. But you can see that, okay, that's going to be of use. If I know one distance, I can calculate the other distance. When they finally calculated the distance between the Earth and the Moon, they just had to times it by 400 to get the distance of the Sun. But we don't go into how they did that. But they still worked out the distance with triangles, but it's much more complex. So, in any similar right-angle triangles, the sides are always in the same ratio. And that's what we formed. So here's where we say, okay, well, what's the hypotenuse, the opposite, and the adjacent? I said the hypotenuse is fixed. I don't care what happens, the hypotenuse is opposite the right angle. Now, as for the opposite and adjacent, they will vary because it depends on the question. If you're talking about this angle, then this is the adjacent side. Adjacent means next to. The hypotenuse is fixed. Lock it. Hypotenuse is fixed. But adjacent means next to, touching. Opposite means, well, opposite. But with that exact same triangle, if someone instead was talking about this angle, then now this one's the opposite, and this one's the adjacent. So I can't lock in opposite and adjacent till I know what angle you're talking about. It'll be very obvious in any question. Here's a question that says, look, here's a triangle. It doesn't matter whether it's upside down or what, or to scale. That's not a good triangle, but I've said that's a right angle. And it says, look, here's 15 degrees. Instantly I'm saying, well, you're the opposite. I knew that you were the hypotenuse and you're the adjacent. Okay? We label it once we know the angle. If we're given both angles, if we're told that that's 30 degrees and that's 60 degrees, they're saying, well, now what do I do? It depends. The question will only refer to one angle. Okay? If you're referring to that one, again, opposite, adjacent. So it will be clear. And these are the basic trig ratios. And sine, cosine, and tangent, we just call it sine, cos, and tan. Okay, they're just their abbreviations. And all it means is, it depends which side we're talking about. It sounds much more technical than it. Do I have a picture on here? So if I'm talking about that same triangle, which is a 2 there and a 1 there and a 30 degrees there, well, while we're at it, let's work out what the other side must be. I know that I'll call that x for a minute. The hypotenuse squared will equal that side squared plus that side squared. 2 squared is 4 equals x squared. 1 squared is still 1. Take 1 off. 3 equals x squared. And square root both sides. X equals root 3. Rightio. If I look at that triangle where I know that, say I made it in metres, 2 metres, 1 metre, and root 3 of a metres. It's about 1.73 metres. Well, sine of 30 degrees equals the opposite side over the hypotenuse. Yep, we knew that. Cos of this 30 degrees will equal the adjacent side the one next to it, over the hypotenuse. So if I put that into a calculator, what's cos of 30? It'll spit me out a horrid-looking 0.866 sort of thing. It's root 3 on 2. That's just what it is. Tan, well, it's opposite over adjacent, 1 on root 3. So again, we don't need to go, the calculator's going to spit it out. But if I type in sine 30, it'll give me a half. If I type in cos 30, it'll give me that, and tan 30, it'll give me that. So you can see all they are as ratios. It says for every 1 length, that side will be 2. For every root 3 lengths, that'll be 2. But it's all in the calc. And we use SOHCAHTOA just to help us remember what goes with what. Or this might be a nice way to think of it. Sine is opposite over hypotenuse, cos is adjacent over hypotenuse, and tan is opposite over adjacent. And that's, a large part of what we're doing this week. This is basic right-angled trig, and we have to know SOHCAHTOA. Or write on the Zor sheet. It may already be stuck in the head. I don't know if you've got any others. Some old hags can't always hide their old age as a mnemonic to remember it. Some old hippie caught another hippie tripping on acid. Has anyone got any others? Yeah? Sex on hard carpet always hurts the other's ass. That's how you learn about sore asses or about SOHCAHTOA. You learned that at school? Yeah. Disgusting. Okay, let me just write it down. Sex on hard carpet always hurts the other's ass. Thank you. I've heard others, but I've never, that's pleasant surprise. Let's go on Facebook. Okay, so again, that's a story. What's sine 30? It's just a half, fine. We're just talking about ratios. All of the trig ratios are just numbers that are already pre-programmed in the, actually that's not true. I'll look that up too. I'll get back to that. Here we go. My mum used trigonometric functions, pre-calculator, and despite what you may think, I've always had a calculator at my schools. But that was, they were given tables. And so you could see from those tables that, once again, they were just ratios. And so if someone said, well, what's sine of 30? They'd go, well, here's just an enlarged bit, sine of 30. And there it was that beautiful, perfect 0.5. Most of them weren't so nice. What's cos of 30? 0.866. Okay, where'd that come from? Well, it's actually root 3 on 2, but 0.866 is an approximation to it. So yes, they got that, and they were able to do these trig things. Now, the calculator doesn't actually have that table programmed into it. There is a formula, so the calculator just works it out. But we can just think, what's the calculator? It's just all of them. It's just got that programmed into it. Fantastic. Which trig ratio would I want to use in that one? Sine, cos, or tan? Tan. Now, I've written it, I don't know whether it's particularly annoying, but I've written it sort of upside down, not the standard triangle where we go yoink, yoink, there you are. No, but clearly that's the hypotenuse opposite the right angle, and we're not dealing with the hypotenuse. Now, whenever we're doing trig, we've always got 3 things, but one of them's unknown, okay? So unknown, got. I've always got to know 2 things and 1 unknown. Sometimes I'll know 2 sides and not know the angle. Sometimes I know the angle in a side and not know the other side. It's either of those 2 scenarios, that's it. So, yeah, that's opposite, and that's adjacent. I'm not using hypotenuse. So SOHCAHTOA is the other's arse. So it's tan is opposite over adjacent. Yep. Okay, we'll get plenty enough practice through here, just as long as we can label what's opposite, what's adjacent. What's hypotenuse? We're gold. Oh, that's just back to that slide. We said that before. How did they know that was 1 to 400? Because they made trig tables. They got a triangle that was smaller that had these degrees. If I go to my calc and say, what's sine of 0.14? It tells me 0.00244, which is approximately 1 to 400. Okay, so that's where that came from. All right, finding an unknown side. This is just this is what we do. Here's the basis of trig. Determine the length of AB. Okay, compared to the angle we've got discussed, well, this is the side AB. It's from A to B. Sine, cos or tan, well, I've got opposite, and I've got hypotenuse. That's the first SOH. S-O-H. Sine is opposite over hypotenuse. So the first thing I do, even when we get to doing the angle, sometimes the angle won't be known, the first thing I do is just write sine, cos or tan equals something over something. Sine of this angle equals opposite of AB over hypotenuse. That's perfect. Now, the AB is on the top, which is easier, but I want the AB by itself. How do I get rid of that divided by 4.9? Times by 4.9. So that just goes over there. Again, it's a very small bit of algebra, but it is algebra. And then that goes straight to the calc. Now, 4.9 sine 27 in the calc will do. You don't have to press the degree key, because like I said, it knows its degrees. Won't matter if you do or don't. You don't have to put the times there between the 4.9 and the sine. It knows it's the times. So 4.9 sine 27 equals, gives me, well, I've rounded already, 2.2 metres. Yeah. Okay, so there's the length of AB. Now, note that if I had been, I'll only do this once. If I had been given both angles and said, oh, well, now what do I do? I'll just erase that. If that's 90, then these two must add up to 90, because the whole thing adds up to 180. So what's that? 63 degrees. It's true that I can work out that angle, because 63 plus 27 plus 90 is 180. You're saying, well, which should I use? Just note, I could use cos if I want. I could say cos of 63 degrees and cos CAH is equal to the adjacent, which is AB, over the hypotenuse, which is 4.9, times the 4.9 over 4.9 cos 63 equals AB, which looks like, well, that's totally different. Here we said it's 4.9 sine 27. Here we said it's 4.9 cos 63. It's the same thing. Okay, it's not suddenly going to change. Sometimes you've got options. Okay, if you know both angles, just pick one. Ignore the other. In this case, I've made that up. But don't be put off by given both angles. Just pick one, and it's going to be correct. Promises. But in this case, yeah, of course I'm going to use that one. Why bother calculate the other one and change to cos? We're going to just use that one and use sine. Unknown in the numerator. Unknown in the numerator. Yep, same heading. That's useful. Okay, determine the length of xy. No real difference here. It's probably going to be a different trig ratio. I've got to put some minutes into the calculator. Neither this too off-putting. xy is old mate here. So sine, cos or tan, well, this is hypotenuse, and we're not dealing with it. So it's SOH, not CAH, not TOA. It's definitely TOA. So tan is equals opposite over adjacent. Tan of my angle, my whole angle, equals opposite of xy over adjacent of 2.4. Yep, pretty version. 2.4, still the unknown's up the top. All I've got to do is multiply the 2.4 over, and then it goes straight to the calc. 2.4, 10, 36 degrees, 20 minutes. There's no brackets needed around it. It knows what's happening. But I did need to press the degrees minutes button after each. So, yeah, 36, press it, and 20, and press it again. Okay. 1.8 centimetres, I'll put the units back, everything's good. Okay. I had an error in the slides. I think it was the X and the 8.2, apologies, my bad. I think they're in the wrong way. Can you just swap them? They are. Can you just swap them? The X was meant to be down the bottom, and the 8.2 was meant to be the hypotenuse. Okay? So on my picture for the lecture example, on this, what page is it, anyone? Just overall. Sorry? 15? Okay, so to swap them. And no, it's incredibly rare that we have typos. That's the only one we've found so far, but I do stick them straight into the course reader typo thing on Blackboard. There's a little thing that says course reader typo whenever I find one. If you ever look up an answer and think, is that correct? Check if there's a typo in there, and then email me. Okay, unknown in the denominator still. Oh, what am I doing? Let's do it. Find x to one decimal place. Fine. X, sine, cos, or tan. Cos, it's all cos. I'm not using the opposite side. I don't want any of SOHCAHTOA with the O's. I want the adjacent and the hypotenuse, which is cos, CAH. Cos of my angle, CAH equals adjacent, which in this case is x, over the hypotenuse of 8.2. Yep, the 8.2 multiplies over, 8.2 cos 12 degrees equals x. Straight to the calc. 8.2 cos 12, 8.2 cos 12 equals 8.02 blah blah blah. 8.02 blah blah blah. I'm not rounding the zero up. It's just 8.0. No. And units, yes we have. I didn't write 1 dp because I just did what it asked. If it said find x, I would have written what I did. But if it said find x to 1 dp, me just writing 8.0 is just doing what it asks. So I don't have to rewrite it, state what I did. The question stated what to do. Unknown in the denominator. Okay, this is just, the only difference here is just a slight extended algebra, that's all. And there's still a shortcut, but we'll check. Determine the length of xz. Xz is old mate here. So we don't have the opposite side, we're cos again. Cos of the angle equals the adjacent over the hypotenuse. So the difference in this question is, and remember it's not x times z, that's not what I'm trying to say here, it's just, we're just labelling the side xz, that's its name. We can do it in 1 step or 2 steps. If I do it in 1 step, I could do exactly what I did before. That xz is on the bottom, same as a number used to be on the bottom. How do I get rid of it? I times that over here. So I could write this, xz cos 20 degrees equals 15.6. That's not really what I want. I'm glad there's no fractions anymore. My second move would be, if I want xz by itself, let's divide both sides by cos 20. Okay, because it's timesing. So xz equals 15.6. Why can't I write? 15.6 over cos 20 degrees. All right. That's not too bad, it's just fractional. But also note what really happened. They swapped. The xz came up to the left and the cos 20 went down on the right. If you want to do that in one go, it's always going to work. All right? So you can either do it in the 2 steps. What did I do in the pretty version? I did 2 steps. So in the book, it's got the xz coming across, then the cos 20 going under. But if you notice that it's always going to be a swap of them, it's all good. Either way, when the unknown's in the denominator, I'm always sticking a fraction into the calculator. 15.6 divided by cos 20, not times, which is 16.6. There were no units given in the question, so I didn't need to put any in the answer. All right, so there's the only difference between unknown in the top and bottom. Becomes that fractional. The one we've got an example, hypotenuses are always on the bottom. We never have a hypotenuse on the top. If there's OH and there's AH, yep, hypotenuses don't go on the top. Compared to this angle, I've got opposite and hypotenuse. I don't have adjacent. So the OH one, what's that? Sine. So sine, I know also, I mean you can say sin. We look at it sin, we've just taken the E off, we've just shortened them all to 3 letters. So it's sine, and cos is cosine, and tan is tangent, but just sine cos tan, that's all we need. Sine of my angle equals opposite over hypotenuse, 78 over y. Also note, I never put units in here, that just gets confusing. Putting letters in there, I just stick the letters back in at the end. Anyone would, that will come back in at the end. Again, I can put in the middle step, if you prefer, times both sides by y, and then get rid of the sine 63, 78 over sine 63, or I could have just said, I know you're doing that swap thing again, and 78 divided by sine 63 is 87.54 blah, blah, blah. So it's spit out 87.54 blah, 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 blah meters. The nearest metre, what's that for this one? 88. Nearest metre means just give me a whole number of metres. Is it 87 or is it 88? 0.5 says up you go. 88 metres. Again, since it said to the nearest metre, I don't have to state it. I answered your question. It's 88 metres to the nearest metre. So, yeah, if the unknown is in the denominator, it's just, I know I'm putting a fraction into the calc. That's all. Ooh, 10 minutes. it's relative to the angle. Here's the angle. It's not adjacent to the angle. It's directly opposite the angle. Adjacent means it's next to and touching. So that's the hypotenuse. Out of the choice, which one's closer to the 20? The 15.6 is adjacent, but the 20, this side is opposite.
So it doesn't mean that. So it doesn't mean that if there's a number that's not adjacent.
No, the number could be either. So it just says, look, it's all about this angle. This is the hypotenuse, so it's locked in. Which side is adjacent to this? This one. So the 15 has to be the adjacent, and the unknown has to be the opposite. So nothing to do with which one's numbered, just where are you compared to the angle. Sweet. Okay, carrying on, we've done the bulk of it now. What we're going to do now is look at how to find the angles, but it's the same starting point. Everyone, please? Everyone. Okay, so now we're just going to, it's the same starting point. We're looking for three things. Side-side angle, which is all Trig's about, but in this case we're going to know two of the sides and not know the angle. But the starting point's the same. First we've just got to say, how do we put stuff into the calculator? Put sine 30 into the calculator. This is just saying we don't need the degree. Sine 30 is just sine 30. Great. Sine 30, we're done. This is what we're about to have to do. So we'll explain what sine minus 1, 0.5 in a sec. We call it sine inverse. But on most calculators, or I think on all calculators I've seen, whether you've got a shift or second function button, whatever, your sine button should have some writing, sine to the minus 1 behind it. So we're going to refer to this sine inverse button soon, and you'll just get it by going shift and then that button. Let's see why we're going to talk about it first, and then we'll check it. Okay, find angle ACB. ACB is that one. Okay, so again, opposite adjacent is just compared to what angle you're talking about. We know that this is the hypotenuse, and compared to this angle, 6.9 is opposite. So we want the one that doesn't have adjacent, opposite and hypotenuse, that's the first sine, So the first thing I wrote down is it's sine. And I always write sine of an angle. Sine by itself means nothing. Sine 30 equals a half. The word sine, it's got to have an angle. An angle here is, well, I don't know, sine angle ACB. And I'll admit, if I was doing this myself, again, I wouldn't want to write angle ACB constantly. I'll just stick a theta in there and call it sine theta. But we'll do that in our own example. Sine of that angle equals opposite over hypotenuse. Opposite is a 6.9, hypotenuse is a 10. So, pretty version. Yep, there's our first statement. It's exactly the same as when one of the sides was unknown. We just wrote sine of an angle equals opposite over hypotenuse. Now, we don't need to get rid of that 10. Before, when we had a fraction, we wanted to get rid of it. No, the only thing I want to get rid of is the word sine. And like I said, the word sine, I can't divide by the word sine. That doesn't make any difference. The opposite of sine is inverse sine. It's exactly the same as the opposite of square root is square, the opposite of times is divide. If I take the sine of something, the opposite of that is taking the inverse sine of it. So I doubt I wrote it here, but what I'm saying is if I took the sine inverse of the left and the sine inverse of the right, whatever sine inverse means, they should still be equal, because I'm allowed to do the same to left and right, but the sine inverse of sine something just cancels it out. So that suddenly isn't there anymore, and all I'm left with is angle ACB is equal to the sine inverse of 6.9 on 10. So I'm not normally going to bother writing sine inverse in front of both sides, but all we've got to think of is if you've got a sine on the left, if you want it going to the other side, that's okay, but it will become a sine inverse. It will become its opposite. And we're always doing that in algebra. Do the opposite of this function if you want to put it on the other side. So sine of an angle equals that, the angle equals sine inverse of that, and then we're just calc. So the sine inverse of 6.9 on 10, you could call it 0.69, it doesn't really matter, you might want to minimise it. I'm just going to do this sine inverse, shift sine of 6.9 on 10. Now it's already opened up a bracket for me, so 6.9, I could do divided by 10, I could probably fraction 10 it. Yep. Oh, don't put the bracket in there. Don't write 9 there. Yep, whatever. And because we're in degrees mode, it spits out in degrees. If we're in radians mode here, you'll see a very odd output, okay? It would make no sense. 43-ish degrees makes sense to me. Let's go back to here. So it spat that out on the screen. Now, with angles, sometimes it'll say give it to the nearest degree, give it to the nearest minute, give it to the nearest second. If it doesn't state what to do, let's just make it easy on ourselves. Like, what have I done here? I could press the degrees minutes button, and it'll show me in that way, and I could round that if I wanted. Or, this is what I'll do. I'll just call it 43.6 degrees to 1 decimal place. If no one's told me to go to degrees, minutes, seconds, I can easily see that 43.63 blah, blah, blah is just 43.6 degrees. So you don't have to express an angle, degrees, minutes, seconds, that'll do. But you could. I probably wrote another answer. That's correct too. I could have done 43 degrees 38 minutes to the nearest minute. Why 38? Because remember that 48 is out of 30. So it was above the halfway. Even though 48 thinks, oh, that's less than half. No, it's more than half because it's over 30, 30 or over. So they're both correct. Again, throughout this semester, if it doesn't tell you how to round something, do what you feel and just write what you did. So let's do another one. Okay, now notice there's no units in this. Sometimes there will be. If that was metres and that was metres, if that was kilometres and that was kilometres, if they're the same units, when I do the ratio as 3.4 over 6.2, as long as they were the same units, I don't really care. The angle's going to be the same. No matter how big or small I draw this triangle, the units don't matter, as long as they were the same. If that was 6.2 kilometres and that was 3.4 centimetres, okay, we've got an issue. But we're not chucking that at you. We're not trying to get you to convert measurements in the middle of trig. Find angle XYZ. So first I've got to work out, I could work out either here, but XYZ, all right, it's this one. Okay, and I will shortcut. This one's already in the notes, but I know that I would rather say, you can be alpha today, XYZ. Sine, cos, or tan, opposite, adjacent, it's a TOA. So I'll be saying that tan alpha is equal to, the opposite is that, and the adjacent is that. So the opposite of 3.4 over the adjacent of 6.2. 3.4 over 6.2. My next step would be, I know that to get the tan over the other side, totally acceptable, but it becomes shift tan, or technically tan inverse. Okay, so it's tan inverse of that, and then I'm just a calculator exercise. But in this case, I'll just get up, the answers will be behind it. So the calculator spits out that, which again, my answer would be 28.7 degrees to 1 dp. That'll do me, because it didn't tell me what to do. So there's my answer, 28.7 degrees. I could also have done 28 degrees, 44 minutes to the nearest minute. I didn't round it up because it was less than 30. All good, but that's me. All right, I assume a lecture example. Find theta as the nearest minute. Clearly, compared to theta, I've got the opposite and the adjacent. I have no hypotenuse, so it's tan again. Okay, tan of my angle theta equals the opposite side over the adjacent side. Yep, same starting point as all the others. Theta, well, you can become by yourself, if I do a tan inverse of the other side. Says to the nearest minute, so I'm stuck here to do it. Tan inverse 19 on 15. So I've got tan inverse, shift tan, 19 on 15. Do I need to finish the brackets or will it do it? Yeah, it doesn't care about finishing the brackets. So I've got myself 51, I'd like to call it 51.7 degrees, but it's said to the nearest minute. So I better press the degrees, minutes, seconds button. On a sharp, I think it's a shift and then this button to convert it. 51 degrees, okay, my decision is it 51 degrees 42 or 51 degrees 43? Is that a round up or leave? 35 out of 60, that says up it goes. That's a 43, 51 degrees 43. Yep, it was followed by 35 out of 60, so I've changed my 2 elegantly into a 3. Round it up. And again, I don't state it because I've answered the question. Find theta the nearest minute. That. Okay. Probably another. Find angle ABC to the nearest degree. ABC, I'm going to do it again. You can be beta this time, just cause. And sine, cos, or tan. I don't have the opposite. So sine, cos, yep. Cos is the one that doesn't involve the opposite. Cos is AH, yep. I've got adjacent and hypotenuse. And check, it could be easy getting around the wrong way, but hypotenuse is always opposite the right angle. So I've got a hypotenuse. Adjacent means next to. Yep, I've got adjacent. I don't have opposite. So it's cos, whoops, not just cos equals, cos of some angle. It's always got to have an angle. Cos of what I've named beta equals adjacent, 7.01, over hypotenuse of 7.84. Beta will equal cos inverse of the same thing. I never bother to put 7.01 over 7.84 into the calc. Why stick that in, then write that down? Just straight to the calc would do. Cos inverse, so shift cos of 7.01 over 7.84. It's spitting out, my calculator says 26.602, you know. I would never bother writing it down, I'm just showing you what it says. It says the nearest degree, I don't care about minutes and seconds. 26 or 27? Followed by a 6. You'll be at 27 degrees. And again, yep, done. All right, so hopefully Trig's looking pretty good as long as we're confident about opposite, hypotenuse, all relative to the angle. Doesn't matter what you're given, it's just relative to the angle. Now this one, I've chucked a couple of semi-curly ones in there. The gut instinct on that one is, well, you said we're doing a right-angled triangle. Where's the right angle? It's not a right-angled triangle. So how can we be asked about this? Yep. And technically, well, we haven't gone through all of the geometry stuff, which I really dislike. But what's that mean? That and that, what's that telling us? Yep, same length, equal lengths. So yes, if we cut this in half, we know that since that length was equal to that, we had an isosceles triangle. Neil's watching, we don't have to care about the word isosceles, but yeah, we've got an isosceles triangle. This thing is perfectly symmetrical. I can't not be symmetrical. If I've got two side lengths the same, no matter where I put them, it's symmetrical. It gets cut straight in the middle, so we do create a right-angled triangle. Okay? Two right-angled triangles, really. So all I've got to do is say, well, if I've cut, that's not 15 anymore, I've cut it directly in half. That's what happens to an isosceles triangle with a line down the guts. So we have got it down to, yep, we can find theta from just half of it. Sine, cos, or tan? Yep. I think there's a cos there. We don't have the opposite. The opposite is the line I introduced. We don't have it. I could find it with Pythagoras' theorem, but why bother? We've got what we need. We need three things with one unknown. Two sides at an angle. We've got everything we need. We've got the hypotenuse here, opposite the right angle. We've got the adjacent here, adjacent to the angle we're discussing. We don't need the opposite. So it's cos of my angle theta equals the adjacent of 7.5 over the hypotenuse of 8.6. So theta will equal cos inverse. By the way, I should state it just in case. There is a x to the minus 1 button on the calc. And for those who are in Sem 1, we were saying stuff like 7 to the minus 1 is 1 on 7. That's still true, but this minus 1, unfortunately, is different. It's really irritating that they've written the same. But just if you see a minus 1 button or you think, does cos to minus 1 mean 1 over cos? It doesn't. It's a bad bit of maths. Just think it's shift cos, okay? It's good old shift cos. Cos inverse of 7.5 on 8.6. Cos inverse 7.5 divided by 8.6 equals, it's spitting out a 29.297 and all that. Okay, we just want correct to one decimal place, so I don't need to convert to degrees, minutes, seconds, just degrees will do. It's followed by, say, 29.2, there's the 1 dp. I really should write meter, shouldn't I? So to 1 dp, that 2 does go up. It's followed by 9. So it's 29.3 degrees. Yep. Correct to 1 dp. All right, so that was one of the curly ones. I'm pretty sure the next one is a bit too. But it helps explain trig a little bit. Yeah, it is. There's probably quite a few ways to do it, but there's two main ways that I can see in looking at it. In triangle ABC, right there, tan A equals 3 on 4. Well, let's mark that in. Tan of A, so we're talking about this angle, equals, tan means opposite over adjacent, so opposite over adjacent is a ratio 3 over 4. So this info told me that. I'm not saying that's 3 metres and 4 metres, I'm just saying it's 3 whatevers, it's 4 whatevers, but yeah, that triangle is in the ratio 3, 4. What is sine A? Can anyone spot anything, any direction to go with it? Because if I'm going to say sine A, sine is opposite over hypotenuse. So someone might have just said it then. I mean, I could, the long way about it would be, could I work out angle A? If tan A equals 3/4, could I say A equals tan inverse 3/4? Yeah. And then find out some horrible angle, and then take the sine of it? It'll work, but there's a nicer way. What's the length of this side? We could work that out. It's that pretty little triad I put up before, 3, 4, 5, or just use Pythagoras. But if you ever want to know the third side, just because we've left Pythagoras at the beginning, we're now in trig, I want to know that side. All right, Pythagoras' theorem. I'll just call it h for hypotenuse. Hypotenuse squared equals one side squared plus the other side squared. In other words, hypotenuse squared equals 16 plus 9. Hypotenuse squared equals 25. We can see, yep, this was that nice 3, 4, 5 triangle. The square root of 25 is 5. So after all of that, I do have a 3, 4, 5 triangle. What's sine of this angle? So, sine A equals 0 on H. I mean, O on H. The opposite side from A is a 3. The hypotenuse is 5. We've done it. Notice it didn't ask me what's A. A would be sine inverse of 3/5. A would also be tan inverse of 3/4. It asked me what sine A equal to. Sine A is 3/5. Oh, shot. So what's cos A? Cos A would be adjacent on hypotenuse. Cos A is 4/5. Okay, so we could get asked any of them. What's sine A? 3/5. What's cos A? Adjacent over hypotenuse. What's tan A? 3/4. Okay, they're all just ratios. Yep. Okay. This is just a reminder that assume knowledge. I'll put in there just in case, well, maybe I shouldn't assume some things. That the three angles of a triangle always add up to 180, okay? Yes, that may be needed in some of these questions that we hit. And note that if we're talking about a right-angled triangle, if 90 plus b plus c equals 180 and I take 90 away from both sides, it just makes it even easier. If you've got a right-angled triangle, if that's 90, these other two must add to give 90. They've got to. So if I've ever got a triangle, I'm saying, well, it's right-angled, and that's 10 yeah, good picture. And that's 10 degrees. Well, I know the other one's going to be 80 degrees because they've got to add to give 90. If there's already a 90, the other two must add to give 90. So as long as we know that all three add up to give 90, yep. Hence we're writing, oh, okay, already did that. Hence we're writing a triangle, the two other ones equal 90, absolutely. And this one, we don't need to know the name ordinate angles, but because of what we're about to do, angles of elevation and depression, looking up and down, sometimes you get this Z shape. And it's good just to see logically that if you get yourself a Z shape, in other words, this is parallel to this, your two little corners are going to be equal. Hope you can see on that diagram, yeah, I believe they're going to be equal, okay? So if I've got a situation like we'll have in a sec when I'm drawing some of these pictures, when we're getting applied, a man standing there looking up at the top of a tree, well, or if someone's on, here's a building, and a man's happy, but standing, there's a railing, and he's standing on the building, and he's looking down at a tree. Well, I might say, we're about to say that his angle of depression, that's leading to, no, is 22 degrees maybe. Okay, which means he's looking down off the horizontal by 22. What this slide's telling us is, if you want to use this triangle down here, that's 22 as well. If he's looking down at the tree and it's 22 degrees down, the tree can look up at him. He's 22 degrees up. It just creates a Z shape. Okay, so let's move on. That's a concept of this. So angles of elevation, depression, it's really no different. We've got some wording, but it's just ways to talk about real life stuff. And again, clearly that's what the ancient Egyptians and Indians and Babylonians and all that were doing. Angles of elevation, depression, and triangulating, working out that angle, that, certain known things. So the main thing here, the point of this slide is, it's always from the horizontal, okay? If someone's looking out straight ahead and then looks down, this is not the angle of depression. It's not the angle off the vertical, it's always off the horizontal. So always think about elevation, depression. The standard is I'm looking straight ahead and either look up a bit and count this angle, or I look down a bit and count this angle, always off the horizontal. So, Joe stands 40 metres from the base of a tower. The angle of elevation to the top of the tower is 28. What's the height of the tower? Now, I'm sure I've got a pretty picture, but often we won't. So we're talking about, and keep it basic, like there's certain things we could get into, like nitpicking, like, oh, how high is Joe? Her eyes are off the ground. Is the ground flat? You know, just keep it really simple. Yes, it's flat. Here's Joe. Here's a tower. The angle of elevation to the top of the tower is 28, as in from her to the top. Not bad, it's 28 degrees. That's much bigger than 28. We don't care, you know, scale is not our issue here. All right, what's the height of the tower? She stands 40 metres from the base of a tower. What's the height of the tower? So nowhere in this question do we want the hypotenuse. Ignore the fact I just used the letter H, that was for height. I've clearly just got a tan situation. My unknown is in the numerator. It's a pretty happy question where we'll go to the pretty version now. Yep, oh, Joe is a bloke. 40 metres, 28 degrees, H. Yep, all good. So tan of 28 must be opposite over adjacent. It's not the fraction one. The 40 can just come over. I can swap sides. H is 21.3. Okay, 40, 10, 28. I'll put my metres back, the units. That's good. And again, the main trap is that was never 28 degrees. It was compared to straight ahead, going up. 28 was measured off the horizontal. Another one. From the top of a cliff, 220 metres above sea level, a woman observes a boat. This is the most places where people will put 32 here. But just compare it. She's either looking straight ahead or she puts her head down a bit. That's the angle of depression, how far she craned her neck. 32 degrees. And this is where I could draw a triangle here. Nothing wrong with that. I've got myself a right angled triangle and I could play with that triangle. Or I could say, well, if you're 32, you're 32, and I'll just play with the triangle that's already drawn. Makes no difference. Who cares? Okay? It might change the trig you use, or it might change what's on the top and what's on the bottom, but it absolutely doesn't matter. So what have I done here in this question? Yep, I did that. I said, well, I've got myself a Z, you're 32 degrees, so I'm just going to use this triangle here where I've got the opposite side, I've got the adjacent side, and I know nothing about the hypotenuse length. So it's tan again. So 220 on D. Tan of my angle is equal to the opposite on the distance. And how far is a boat from the foot of the cliff? Again, if it said how far is the boat from the cliff, you might think, oh, well, from her or from that? No, it's from the foot of the cliff. It's always the shortest distance, okay? So 32, yep, so the D comes across, and the 1032 goes under, either in one step or two. I've done it in 2 steps. Multiplied both sides by d, divided both sides by 1032, and then straight to the cap. 352 metres. Great. My picture wasn't perfectly to scale, but it was something similar. But again, okay. Elevation, depression. So now the last two, we'll just make it ourselves. A ship is sighted from a plane at an angle of depression of 34 degrees. The diagram's often going to be the hard thing. A ship is sighted from a plane, and if you start these things out like thinking, all right, here's a ship, and here's a plane, and then thinking, oh, well, I don't know. If you put it directly above it, yeah, I'm in trouble already. It's not directly above it. Its angle of depression wasn't 90 degrees down. No. Okay. Here's a ship. Here's a plane. Okay. Here's the plane looking straight ahead, and here's the plane looking down at the ship. 34 degrees angle of depression. Yep. So this can be my triangle. Doesn't matter whether it's upside down or right way up. What else do I know? I've got to know one more thing, and I've got to have one question. There's 3 things in every trig thing. If the distance from the plane of the ship is 5 kilometres, is that the hypotenuse, or sideways, or vertically? Yeah, it's just hypotenuse. It's directly. The distance from the plane to the ship, is absolutely this. We do have the hypotenuse in this question. It's 5 kilometres between the plane and the ship. Calculate the height of the plane to the nearest metres. Well, height, probably, if I was better at writing questions, probably would say height above sea level. Okay? But yeah, that's what's meant. The height above clear, flat sea. In an exam in particular, we make sure others read it and try and work out any way you could misread the question. So I'll definitely say height above sea level. I'm going to change that. Okay. And if that's height is there, well, that's the same height as this one. I don't have to draw this triangle under here. My triangle's good enough. Or call that 34, whatever mood you're in. But at the moment, I'm going to focus on this little triangle I've drawn, and the one I've drawn is a sine. I don't have the adjacent side, and no one's asked me about it or given anything about it. I've got the opposite side and the hypotenuse. So sine of my angle is equal to the opposite side, which is the height of the plane, over the hypotenuse. Apologies again for using h. I'm not using h for hypotenuse. I should stick to my x's. If I don't know it, just call it x. But yep, the opposite side over the hypotenuse. The 5 multiplies over. So h equals 5 sine 34. 5 sine 34 equals... What accuracy did it say? To the nearest metre. 2.795795964 blah, 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 blah. That's what I got out of my calculator. What do I need to do to that? What's that in? Yeah, that's kilometres. I want the nearest metre. I resource sheeted, or maybe I know that there's 1,000 metres in every kilometre. So if I want it to the nearest metre, 1, 2, 3. Hopefully you'd know the 2.79 metres if the height of the plane was that. I'm really, really bad at writing questions. But 2,795.964 blah, blah, blah metres. So what is it nearest metre? Well, it's a 9 that makes the decision. Do I leave the 5 or take it up? Clearly I take it up. 2,796 metres. So the nearest metre is a technicality. If someone wrote 2.796 kilometres, that's still 100% right. That's been rounded to the nearest metre. I'd rather actually just convert it to metres and give a whole number. But I times it by 1,000, convert kilometres to metres. That little 2-arrow thing we used last week, or 3-arrow thing, helps us with that. 2,796 metres, yep. Okay, now the last one is the most complex sort of ones we look at. And again, it's going to come down to drawing the picture. But remember, it is just go with common sense. There's not meant to be any traps going on here. An observer on top of a building. Okay, let's just read through first. An observer on top of a building finds the angle of elevation to the top of a taller building to be 14 degrees. Okay, two buildings. The angle of depression to the foot of the same building is 33. So he's both looking up the top of that one and down the bottom of that one. Buildings on the same ground level. We know the distance between them. All right, here's the ground. I know I've got a building and another building. An observer on top of the shorter building looks up instead of just looking straight ahead. Once again, see, I'm pretending it's his feet looking. I don't care about the height of the person. We're not getting into technicalities. The height of the taller building, well, he had to look up 14 degrees to see the top of the taller building. Angle of depression to the foot of the same building is 33 degrees. All right, so that's what we've got. Either looks up at 14 to see the top or down at 33 to see the bottom. I've got myself two right-angled triangles. We're told the distance between the two buildings is 280 metres. All right, 280 metres. And I want to find the height of the taller building. So I'm just saying, well, if that's 280, this is 280. That's 14 degrees. You don't have to rewrite it. I'm just saying, well, what have I got all up? That's what I've got. 14 up, 33 down, and 280 is the horizontal distance between them. And I want to know the full height. Let's just do that. X and Y. I want them both. But I can see from my little right-angled triangles, I can find X and I can find Y, and I'll just add them. Okay? It doesn't tell me what rounding, so I'll just go ahead and say, with the top triangle, I've got the adjacent and the opposite. So tan of 14 degrees equals X over 280 times the 280. 280 tan 14 equals X. That'll do for the moment. I found X. I'll stick it in the calculator and I found Y. It doesn't matter whether I do it complete or not. The other triangle, what have I got? This angle, I've got tan again, opposite over adjacent. No hypotenuse is happening in this question. Tan of 33 degrees equals Y over 280. Again, the Y's on top, good. I've just got to times the 280. So 280 tan 33 degrees equals Y. Therefore, the height of the building, which is X plus Y, is, I'm just going to chuck them both in the calc, it's 280 tan 14 degrees, the top one, plus 280 tan 33 degrees, equals plus 251.645, 251.645, 9, blah, 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 blah. No, stop. Didn't tell me. Nearest metre will do. 252 metres. Oh, David. Nearest metre. Or I could have written naught dp. You know, your call on what you want it rounded to, but yep, done. Everyone loves trig? Everyone loves GA, yeah. Okay, that's a yes. All right, till shoots. Don't forget, yes, we have a quiz this week on last week's stuff. Okay.